Welcome to today's lesson on product and quotient rules. Hopefully by the end of this lesson you'll be able to state and apply the product rule and state and apply the quotient rule. So we'll start off with the product rule, and we're going to define a function y as the product of two other functions u and v. If we differentiate y with respect to x, then we're differentiating the product of the functions u and v with respect to x. And the way we do this is we say that the function u multiplied by the differential of v with respect to x plus the function v multiplied by the function u differentiated with respect to x. We can write this in function notation instead of Leibniz notation. And we have the function hx is the product of functions fx and gx. When we differentiate hx, we have the function fx multiplied by the differential of the function gx plus the function gx multiplied by the differential of the function fx. And that's the product rule. Hopefully relatively painless, but just to check, we'll go through a worked example. Remember to pause it at the question and only look at the answer solutions if you get stuck. So you need to use the product rule to compute the derivative of the function y equals x squared plus 3x multiplied by the function 2x minus 1. So we start off by writing out our two functions, and we separate them out to the function u and the function v. Then we'll write down the product rule just so that we know what we're looking at. Then function u is written with the differential of function v, which is 2, and function v is multiplied by the differential of function u, which is 2x plus 3. When we multiply that out, we end up with 6x squared plus 10x minus 3. Moving on to the quotient rule. So here we have function y is function u divided by function v. This time the differential of y with respect to x. Function v multiplied by the differential of function u with respect to x minus function u multiplied by the differential of function v with respect to x, and all of that is divided by function v squared. Again, we'll have a look at this in Leibniz notation. We have a function hx is equal to fx over gx. The differential of hx is equal to gx multiplied by the differential of fx minus fx multiplied by the differential of gx. All of that's divided by gx squared. We'll have a look at a worked example for the quotient rule. It's an interesting one actually, because it's the differential of tan x, which is obviously sin x divided by cos x. Same as we normally do, pause on the question, try and answer it, and then if you get stuck, press play to look at the solutions. Like I said already, this is tan x, which is two functions sin x divided by cos x. We'll start off by writing it down nice and clearly. Tan x equals sin x over cos x. U is sin x, v is cos x. So when we carry out that differential, when we carry out the quotient rule on this, we end up with cos x multiplied by cos x minus sin x multiplied by minus sin x divided by cos x squared. So this gives us cos squared x plus sin squared x over cos squared x. From Pythagoras' theorem, we know that cos squared x plus sin squared x is equal to 1. So our solution is that the differential of tan x with respect to x is 1 over cos squared x. This is an important solution, so we're going to put it in our blue box. We're going to get on with some worked examples now. But before we do, I would suggest that now would be a good time to do the other part of your homework today, which was to write down the chain rule, the product rule, and the quotient rule in your own words. So not just the symbol equations, write it down in words. Okay, so play back those videos, play back those parts of the videos, make sure you understand the rules, and write them out using words. And then this is the first of 3 example problems.